The Sun, a seemingly eternal source of light and warmth, is the heart of our solar system. It has been burning for over 4.6 billion years, providing the energy that sustains life on Earth. Yet, this giant ball of fire is far more than just a comforting presence in the sky. It is a nuclear powerhouse, driven by processes that are as complex as they are awe-inspiring. Understanding how the Sun works, particularly the nuclear reactions that fuel it, requires a journey into the realm of astrophysics, where immense pressures and temperatures give rise to phenomena that defy ordinary experience. Equally fascinating is the story of how the Sun will eventually die, a narrative that spans billions of years and ends in a dramatic cosmic event. At the core of the Sun lies the source of its immense energy, nuclear fusion. This process occurs in the Sun's core, where temperatures reach around 15 million degrees Celsius, and the pressure is more than 250 billion times Earth's atmospheric pressure. Under these extreme conditions, hydrogen atoms, the most abundant element in the universe, are fused together to form helium. This fusion process is not just a simple combination of atoms. It involves overcoming the electrostatic force that normally pushes positively charged protons apart. When the hydrogen nuclei, protons, collide with enough force, they fuse together in a series of steps known as the proton-proton chain reaction. The proton-proton chain reaction is the dominant fusion process in the Sun, and it can be broken down into several stages. First, two protons collide and fuse to form a deuterium nucleus, which consists of one proton and one neutron, releasing a positron, the antimatter counterpart of an electron, and a neutrino, a nearly massless particle. The deuterium nucleus then fuses with another proton to create a helium-3 nucleus, two protons and one neutron, releasing gamma rays in the process. Finally, two helium-3 nuclei collide and fuse to form a helium-4 nucleus, two protons and two neutrons, and release two protons. The entire process releases a tremendous amount of energy, which manifests as the light and heat that we receive from the Sun. This energy is the result of Einstein's famous equation, E=mc², which shows that mass can be converted into energy. During the fusion process, the total mass of the resulting helium nucleus and the other particles is slightly less than the mass of the original hydrogen nuclei. This missing mass is converted into energy, which radiates outward from the Sun's core and eventually reaches Earth. Every second, the Sun converts about 600 million tons of hydrogen into helium, losing about 4 million tons of mass in the process, which is released as energy. Despite this massive consumption of fuel, the Sun has enough hydrogen to continue burning for billions more years. The energy produced in the core travels outward through the Sun's radiative zone, where it is absorbed and re-emitted countless times by the surrounding plasma. This process is incredibly slow. It can take thousands to millions of years for a photon generated in the core to make its way to the surface. As the energy moves through the radiative zone, the temperature and density gradually decrease until it reaches the convective zone, where the energy is transported by convection. In this outer layer, hot plasma rises toward the surface, cools, and then sinks back down, creating convection currents that bring the energy to the Sun's surface, or photosphere. The photosphere is what we see when we look at the Sun, and it has a temperature of about 5,500 degrees Celsius. This is where the energy is finally radiated into space as sunlight, which includes visible light, ultraviolet radiation, and other forms of electromagnetic radiation. The Sun's light takes about 8 minutes to reach Earth, and it is this energy that drives our climate, weather, and supports all life forms through the process of photosynthesis. However, the Sun's ability to sustain nuclear fusion is not infinite. As the Sun continues to burn hydrogen in its core, the proportion of helium increases, altering the balance of forces within the star. Eventually, the core will accumulate so much helium that it will no longer be able to sustain hydrogen fusion at the same rate. When this happens, the Sun will enter the next stage of its life cycle, which is far less stable and more dramatic. As the hydrogen in the core is depleted, the core will contract under the force of gravity, causing its temperature to rise. This increase in temperature will ignite hydrogen fusion in a shell surrounding the helium core, and the outer layers of the Sun will expand dramatically. The Sun will swell into a red giant, engulfing the inner planets, including possibly Earth. In this red giant phase, the Sun will become much cooler on the surface, which gives it a reddish hue, but it will be vastly larger and more luminous than it is today. The red giant phase is a relatively brief period in the life of a star like the Sun, lasting only a few 100 million years. During this time, the core will continue to contract and heat up until it reaches temperatures high enough to ignite helium fusion. This process, known as the helium flash, occurs rapidly and results in the conversion of helium into carbon and oxygen in the core. The energy released by helium fusion will temporarily stabilize the Sun, but this phase will also be short-lived. Once the helium is exhausted, the Sun will be unable to sustain fusion in its core, leading to the final stages of its life. Without the outward pressure generated by fusion to counterbalance gravity, the core will contract further, becoming a dense, hot remnant known as a white dwarf. The outer layers of the Sun will be ejected into space, forming a planetary nebula, a glowing shell of gas and plasma that can be seen across vast distances in the galaxy. The white dwarf at the center of this nebula will gradually cool and fade over billions of years, eventually becoming a cold, dark, and inert object known as a black dwarf. The death of the Sun, while inevitable, is not something we need to worry about in the near future. It is expected to enter its red giant phase in about 5 billion years, giving life on Earth plenty of time to adapt or relocate. However, the fate of the Sun serves as a reminder that even stars have finite lifespans and that the universe is in a constant state of change. The story of the Sun, from its formation in a cloud of gas and dust to its eventual demise as a white dwarf, is a testament to the power of nuclear reactions and the intricate balance of forces that govern the cosmos. These processes, while distant and seemingly abstract, have direct consequences for life on Earth. The Sun's energy sustains our planet, drives our climate, and shapes the environment in which we live. Understanding how the Sun works, and how it will eventually die, gives us a deeper appreciation of our place in the universe and the transient nature of all celestial bodies. In the grand scheme of things, the Sun is just one of countless stars in the universe, each with its own life cycle and story. But for us, the Sun is special. It is the source of all life on Earth, the star that has allowed civilizations to rise and flourish. As we look to the future, we must consider the long-term implications of the Sun's life cycle, not just for the fate of our planet but also for the broader questions of life in the universe. How will humanity adapt to the changes that lie ahead? Will we find a way to survive beyond the life of our star? These are the questions that the study of the Sun inspires, as we seek to understand not just how it works, but what its eventual death will mean for the future of life in our solar system. The Sun's journey from birth to death is a reminder of the impermanence of all things in the universe. It teaches us that even the most powerful forces we know are subject to change and that the cosmos is a dynamic, ever-evolving place. As we continue to explore the mysteries of the Sun and the stars beyond, we are not just learning about the mechanics of nuclear fusion or the fate of stellar objects. We are also gaining insights into the fundamental processes that govern the universe and our place within it. The Sun, in all its brilliance and eventual decline, is a symbol of the cosmic dance of creation and destruction that has shaped the universe since the beginning of time.